So let's do an example of bearing wall capacity. So essentially the bearing wall, you might remember, let me click over to the notes, similar to this, if we're just looking at axial, it's the same as a column, other than the fact that we have per foot of wall. The other piece is we only have to look at strong axis bending because we assume that the sheathing that's put on restricts us from weak axis bending, right? The problem we're going to do is going to look at just the stud in the base, it says, but we're not going to look at the top plate. So these two items have to do with the top plate. In other words, I'll show you in the problem. We're just going to look at the column piece of this, the studs. All right, so it says consider stud and bottom plate, and the bottom plate's resting on the ground. The top plate here in this direction, you have to watch between studs if there's, that it meets the flexure requirements and things like that. We're just going to look at the stud because that's the part that's in pure axial. Go ahead and draw section AA here. Let me get my notes in order. So typically your studs are going to be, I'm just marking the 2x4s on here, at 16" on center. Okay, so if you get a stud finder in your house or apartment, if it's this type of construction, you should be able to find the studs at approximately that distance on center through the middle of a wall. We know these are 2x4s, so 3.5 inches here. And if we look over here, we've got 9'6". We're going to be interested in the length. And the length here, if you can see this, it's 9'6" or 9.5 feet minus 1 2x4, 2 2x4s, 3 2x4s thickness. So 3 times 1.5. So if I look at the actual length of this thing, it's going to be, oops. The effective length, we're going to assume K equals 1, or a standard conservative pin-pin connection. So the effective length for this thing is 9'5" minus 3 times 1.5 inches each. Those are the 2x4s here. And convert all this to inches, so I'd have to multiply this by 12 inches per foot. I didn't happen to calculate this separately. It doesn't really matter. All right, so minus 4.5 inches off of here. So let's go ahead and look at our L over D. Oops. Which is what I'm really trying to get towards here. So my L, EX over D in the X direction, or maybe we should use 1, since that's what we've been using for strong axis, is the K, which is 1, L, E over D, this is 1. And so I've got that 9.5 feet, 12 inches per foot, minus the 3 1.5 inch 2x4 pieces there. And then all of that is over the depth, which is a 3.5 inches for a 2x4. And I get 31.3, so less than 50, just like we check for slenderness on the other columns. So we check that. This is, so strong axis controls because of the sheathing on the studs that can keep it from buckling in the weak axis direction. Let's write this down here. So that was something we covered in the notes, but I'm just going to write it down here. So if you're going back and wondering why we didn't check both directions, that's why. All right, so they are actually asking us to find the load capacity, right? So what's P? And we're assuming it's dead and snow load. And they want that capacity in pounds per linear foot. So in other words, instead of looking at a single stud, we're going to look at pounds per linear foot over the wall because that's the load capacity we're interested in coming down from the upper floors. All right, so let's get started on this. So we know that we have to have little f sub c less than what's provided by the section. So the stress in the section is the P over A. We know already that we've got P is what we're going to be looking for. 1.5 times 3.5 gives us that area. And then F prime C, I shouldn't call it F prime C, F sub C prime. We look up the value and then we multiply by all of our factors. Same stuff as always. In this case, we've got F prime C is 1300. If you look this one up, did I give you, oh yeah, in the problem statement, hem for number 2. Here's our 16 OC. All right, so we'd look that up. And then each of our items here, C sub D is 1.15. The rest of those other guys are 1, but I need C sub P. All right, so we've done the C sub P calculation quite a few times at this point. So I think I'm just gonna give you the answer on this one so that we don't, because there's no reason to go through that for a third time. So C sub P in this case is only 0.25. All right, so if you want to do a check along the way, remember C sub P is the long equation. If you want to do a check along the way, you should get F sub CE equals about 394 psi, and you'd get F star C at approximately 1495 psi. Okay, and finally, we know that C is equal to 0.8, and run through that equation that we've done on our previous examples. I'm going to get a CP value of just 0.25, so that's a quarter of what I would have gotten. So that factor is pretty heavy hit here. All right, so F prime or F sub C prime equals the 1300 times 1.15 times a quarter. So only 370 psi. So the P value that I get for a single one of the studs would be 370 psi times the area. So 1.5 inches times 3.5 inches equals 1941 pounds per stud. All right, so about 2 kips per stud. So the max per unit of wall is going to be 1941 pounds, and those are spaced at 16 inches or 1.33 feet, and we get 1495 pounds per linear foot of wall is our max. Okay, so that's our max axial load. All right, so did a back solve for this one to find the load, but given a certain load, you know how to, if they give it in 2 pounds per linear foot, or if they give it per stud, you should be able to go back and check or design the spacing or whatever you need. Now studs we typically space at a certain on center, but certainly you could move them so that they, you know, if this was just a wall where you're trying to meet a certain capacity, probably you would look at taking your load and looking at the different types of wood you could have, etc. All right. That